Hi, this is Mrs. Hammer, and we are just going to do a practice problem here to understand weak acid equilibrium. Basically, the weak acids don't dissociate 100%, and so we're calculating how much they are dissociating and what the resulting pH will be. So this problem says calculate the pH and the percent dissociation of a 0.6 molar solution of hypochlorous acid, that is HCl. And the Ka value is given for the hypochlorous acid. So anytime you're asked to do calculations with a weak acid equilibrium, you just want to set up a rice table. If in doubt, set up a rice table. The R, of course, stands for the reaction, so that's HClO. We do a double arrow, and then H plus and ClO minus. Because we already have that ready to go, we should probably either off to the side or down below start setting up and thinking about our Ka expression. The Ka expression, remember, is the products over the reactants. So it's going to be H plus times ClO minus, and then that's over the reactant. That was the original HClO. All right, so that's our Ka expression. Again, it's always products over reactants. And if you ever have like pure water in the reaction, you just leave that out. All right, so the I in the rice table stands for our initial concentration. So the initial concentration of the acid was 0.60 molar. And we're keeping things simple. Before it dissociates, of course, our concentrations are 0 and 0. Now, in this particular problem, we actually don't know how much it's going to dissociate. And we don't know that because they gave us the K value, and we have to figure out what that tells us about how much dissociates. So all we can do for the changes line is say that we're going to lose some of our acids, some of it's going to dissociate. For every X number of molecules that dissociate, we're going to get that same number of hydrogen and hypochlorite formed. So we just have minus X on the reactant side and plus X on the product side. So now the initial plus the change gives us the equilibrium value. So it's 0.6 minus X for the original acid. And the two ions started at 0, so they're both just X. Now, what we want to do is we want to take this equilibrium line and we want to substitute it into the Ka expression. However, if we substitute it as written, this minus X is going to make our calculations real nasty, real bad. So we want to get rid of that minus X, and we're able to because the amount that it's losing is very insignificant. You can do that for weak acid and base calculations. All right, so I'm going to set up my K expression with substitutions down below. So my K value is known. My K value was given as 3.5 times 10 to the negative 8 equals X squared over 0.60. And so pretty much we're just needing to calculate our X value. So if you grab your calculator and solve for X, which I need to do, we're going to do 3.5 times 10 to the negative 8 times the 0.6 on bottom. And so our first step is we get 2.1 times 10 to the negative 8 equals X squared. So to solve for X, we need to square root both sides. And we get that X equals 1.4 times 10 to the negative 4. 1.4 times 10 to the negative 4 molar. Now we need to go back and make sure we actually answer the questions. It did not say solve for X. So the problem actually said calculate the pH. So I want to point out that the hydrogen ion concentration that's actually produced is equal to X. So instead of having X here, I could also say that equals my hydrogen ion concentration. So of course we calculate our pH value by doing negative log of our H concentration. So that's going to be negative log of 1.4 times 10 to the negative 4. So you just type that in your calculator exactly as is. And we get 3.84. So that's our pH value. So that's the answer to the first question. It also asked us to calculate the percent dissociation. So the percent dissociation is actually pretty easy. It's just the amount that actually did dissociate So in other words, your x value, 1.4 times 10 to the negative 4, divided by the original acid amount, 0.6, times 100. So it's really just part over whole times 100. So 1.4 times 10 to the negative 4th divided by 0.6, and don't forget to multiply by 100. We get a very, very small amount, 2.3 times 10 to the negative 4%. If you didn't want to write it in scientific notation, that would be 0.00023%. So potato, potato, whichever way you want to write it is acceptable. So that's the main idea on how to work a weak acid equilibrium problem. Set up your rice table. That's going to be one of your first most important things. Also, always write the K expression, and then remember that you take your equilibrium values and substitute those into the K expression. That's the way to get started on any weak acid problem. Thanks for watching.